today we have a talk by by Professor Wilhelm Schweiger on his talk will be on zeolitic materials with hierarchical porosity, preparation, concept, and application.
Yeah, thanks very much for the introduction. I have to mention that the talk has changed, and I will give this talk about a hierarchy tomorrow in the plenary lecture. In the former program, it was announced like this, and due to the fact that the organizer asked me to give another talk, I will talk in this nano section about nanomaterials, but not about such fancy ones like the dots we have seen before. It's the old nano-styles materials about silicates and zeolites. And I have mentioned the two co-workers, Albert Machoko and Salvan. Salvan did the work on the silicates and Albert the work on the zeolites. Okay, but I am from Erlangen. Erlangen, where is Erlangen? Erlangen is in the north of Bavaria, in Franconia actually. And what is Erlangen all about? Erlangen has a university, not such that big like Cairo. We have just 40,000 students, but we are a much smaller town. We are just the town of 100,000 persons, and there we have 40,000 students, which is, I think, amazing as well. And we have two campuses, and this is the South Campus, where we are located in the south, and this is this campus in town. This is in the downtown area where we have this castle. Today is the administration building of the university. Yes, this is our institute. Oh, this is still in German, I realize at the moment. This is the Institute of Chemical Reaction Engineering. And Peter Wasserscheid is dealing with complex catalysts and ionic liquids. I deal with heterogeneous catalysis and porous materials, and Hans-Jörg Freund is, is trying to optimize chemical processes in general. And in my group, I have three pillars, and about one I would like to talk today. At the moment, preparation and modification of porous materials. I use microwave and ultrasounds for supporting catalysis, supporting structure formation, and I use ultrasound as a diagnostic tool for the formation of crystalline materials. And tomorrow I will talk about these hierarchical materials, macro, meso, meso, macro, micro, macro, and all combination of this will be given tomorrow. Today I just focus on the zeolites and the silicates. And back to the title. After this small introduction, and bifunctional silicates and zeolites and nanos. In former time, nanos was not nanos. Nanos are obviously very modern. Degussa announced this aerosol as a millimicron, not as a nano at this time. And I found this amazing when I found this, that nanos are not that old, in spite we had nanos, and even in the case of the aerosols, we have very well-defined nanos, and when we go down with the size, we have certainly different surface areas, which is quite important for catalysis. And here you see a term of this very well interfaced in the modeling of such a primary particle, and this primary particle in the aerosol is about 7 nanometers, certainly very small. And so that means nanos are really well known, even in former time when we didn't talk about nanos. And we were talking about colloids, aerosols, millimicrons, and so on. But even layered materials are nano-like materials. At first, I will address two ideas in this talk: how we are going to use layered materials as a support for catalysis, make a use out of the nano functions. And then secondly, I would like to talk about the densification as a new method to produce silicatic nanomaterials. Okay, let's go on. why we are interested from usually the zeolites are purely microporous materials, and the advantage we have shape selectivity, thermal stability, but we have problems. Long diffusion pathways, high selectivity to coke, and pure accessibility of the active sites. This we have to overcome, and this we are going to overcome. We are drawing holes inside of the crystals. We are going to slice crystals, like with the bread, and then we have nano dimension in one crystallographic directions. Here we have the nano dimension between the pores. Or we can really prepare porous materials, and also there we have, let's say, the dimension of the nano particles as the length, the pathway which molecules have to travel in the pore to access the active sites. At the moment I would like to talk about the layered materials, starting which layered materials are known. Layered materials are known in the nature since a long time. We have the layered double hydroxides, I guess Norman will talk about this. We have the clay materials, certainly, kaolinite, montmorillonite as a typical, where we have tetrahedron and octahedron, and we have aluminum phosphates as layered materials, and we have just pure materials which consist just as tetrahedrons, the so-called layered-like silicates. Have a closer look in this, very schematically. The basic unit is certainly the tetrahedrons, and we have the different condensation behavior. Certain tetrahedrons are connected with each other, but let's start on the right side from your side. There we have schematically the tetrahedrons and the octahedrons and the TOT layers in the montmorillonite, or the TO layers in the kaolinite. And then we can have layers where we have every tetrahedron is just perpendicular to each other, and we have on every corner a metal, exchangeable metal. Or we have condensed layers. 1, 2 layers are condensed in one plate to each other, and we have metals and protons there which can balance the charges. And in this layer, I would like to talk about this. We have certainly the bulk layer consists of silicon oxide, pure silicon oxide, acidic stable, and we have to balance the cations, the corners with cations, and we have in between the layers water or some other adsorbents, adsorptives, or whatever. And intrinsically we have something like a 2-4 ratio silicon oxide to sodium in this 2, 4, 8 to 10, 10 to 20, and larger than 20, and named kyanite, magadite, kenyite. This comes from the first origin where we found this, that we have found. And there we have some in between, iodide, group 18, which are just synthetically available. What is the interesting thing? Here you see the typical behavior, very well plain rectangular layers. In this case, octosilicate with the silicon oxide, the sodium oxide of 18, group 18, or 8 iodide. This is known in the literature as well. Or here you have a cauliflower aggregation, but in this cauliflowers even some places. And this is the magadite. And there are some early reports. Euler was reporting about the ion exchange. Lagerli was reporting about the complex formation, intercalation, and we reported about some NMR results about these materials. And originally they were found in the Lake Magadi in Kenya, in the soda-rich lakes, where they were formed in this plant. And if you go back now in the literature, even we were not the first one, and even Lagarde were not the first one. If you go really back in the, if you go really back, Baker was the first one who synthesized the material, but she couldn't identify. But today we can say this is magatite. In 1920, McCulloch was the guy who reported about some silicates with the ratios silicon oxide to sodium oxide about 9 to 30. This was the iodide and the magadite. And Euler, he reported this one. but it was also in 1967 when we found and described these materials from the original sources in the Lake Magali, where we became a little more insight in the structure. Okay, but look at the X-ray diffraction pattern. Very typically, you're going to shift from the magnetite with this lowest ratio to the Kenya eye with to lower angles, which higher thickness of the layers, and in the middle you are going to lose orientation, ordering. And this is going with the row 24822. And in detail, is in the group of Hermann Wies, Michaela Fortmann, really could solve the structure. And you see here we have 5 rings in the layer connected via SEO bond, and on every of these 5 rings you have 1, 2, 3 pH groups, which are exchangeable with the active sites and so on. This is a very typical or unusual structure, but there are some structures solved at the moment. Our kenyite, magadite, and all the H forms and metallic forms are not solved. They are still unknown. We have some proposals, but not really materials. Historically, not really structures, excuse me. Historically, we can synthesize them in the hydrothermally, in this thermal systems, variation of the sodium content, the silicon oxide, the sodium, and the water content can vary. It takes 50 degrees to 2 weeks, hours to weeks, 50 to 250 degree hydrothermal autogen these pressures. And in this region, you can prepare this really in a perfect way. And the kinetic of the crystallization has always an S-shape, very typically for such systems. And you see with the temperature from 80 days to just 20 hours, you can increase the crystallization rate drastically. Temperature is more favorable. But what can we do in respect to nano? These layers, schematically drawn here, have a high ion exchange capacity. What we did, we are starting to exchange this with novel tetraamine complexes, and we could really increase or intercalate a lot of these materials. And finally, usually in catalysis we have a problem to shield these novel metals or to really stabilize these novel metals, and we destroy the layers and encapsulate these novel metals inside the structure. And the idea is we can really vary the thickness, that means we can vary the wall. Or we can really vary the ion exchange capacity, we can vary very systematically the number of metals which we can implement. Oh yeah, excuse me. And here you see some pictures, and these dots are really the noble metal, in this case platinum, in this iodide, silicon oxide to sodium oxide 8, and even after calcination, outside you see some larger particles, but inside you really don't see this. And with a loading of about 28%, which is really huge, and even under this condition very stable. The strategy is very simple. After you have the silicates hydrothermally, it's just the ion exchange process, just at room temperatures to equilibrium and so on, and you can stabilize the novel metals up to 500 degrees inside of this lattice. And this you can see even from this TG measurements. Here you have the plane component, here you have the sodium iodide, and here you have the stages of the decomposition of the, let's say, tetramine platinum complex loaded on the iodide. And you see a shift of nearly 200 degrees, then instability of the complex, but then you have really the loaded material, like you see this here after the calcination. And you don't see any sodium anymore after the ion exchange. You have a really high loaded system. You can adjust certainly the system even if you need such small amounts, it's very easy to find the equilibrium point for the lower loading system. But what you can do, what is the idea behind that? If you have now the platinum is a really is another metal useful for catalysis and especially for bifunctional catalysis. And even in this case, we did the isomerization. There are some bifunctional catalytic constants around. If you have platinum on the zeolite and the acidic conditions, we really can isomerize, for example, hexane. And when we can do this in the presence of hydrogen, but we can do this also if we have activated hydrogen, and we can do the activation on the platinum-loaded materials. What we did now is to prove if we can in one material activate the hydrogen, and in the other can provide the acidic function. We synthesized the iodide, as I told you, we did intercalation, and then we mixed it with a really well-known acidic zeolite, in this case the erionite, and did the catalysis. And what was the outcome? Just briefly. Here we have the catalysis results with the with the erionite, and here is the iodide. And our targeted product is the isohexanes. And if we have just the acidic function, we don't see them. If we have the platinum and the acidic function in the erionite, we see them. Not in the ion exchange form, nothing, no activity at all. But when we do the mixture of the platinum iodide with the H-erionite, so we have the active components, the metal in the other material and the other one. This is just explainable if we assume that we have this spillover, the transport of the activated hydrogen to the acidic side. Yeah, and what the normal system is this one. We have the paraffin, olefin, isoparaffin in the presence of hydrogen. And what we did here, we have the coke formation, certainly on the active sides. If we don't have a hydrogen there, if we can activate the hydrogen now on the other phase, we have the activated hydrogen. And if we are going to activate or increase the direction of the supply number of platinum atoms in the iodide, for example, then we can get the isoparaffin. If we do this too much, if the supply is too high to the consumption, we have a hydrocracking product and we release hydrogen anyway. This means we can now optimize the catalyst by variation of the ratio of the active compounds and the H form using this hydrogen. Okay, the mixture of the iodide and the erionite gives us now optimal conditions for this material. And interestingly, I would add just one resource, this palladium. If you load this with palladium, we can absorb the oxide. If we calcine this in air and nitrogen, we get the real pure palladium component, the metallic component. And even now we can optimize this again, the ratio between them. And here you see again palladium inside of this iodide according to different procedures. If it fails, you see here you have large aggregates on the surface. To summarize this part, I hope I could show you that this principle of the systematic variation of the layer thickness and the charge on the layers is valid. The advantages: you have pure inorganic system, you have stable silicatic system, even in acidic surrounding, and the material itself is mild acidic. And you can combine this with, via ion exchange, with metallic components and make a use out of them to the catalysis. With this, I would like to come to the second part, the densification as a method for the production of the nano-sized zeolites. Now, I will touch few things, principle, experimental, and at least at the end I will show also catalytic results. Again, just to remind you, in all three dimensions, we would really slice the material, we would create nanoparticles and micropores. If you have this length is short, the travel pathway for the molecules is short, and we have huge number of entrances to the active sites. But on the surface, we have also the danger of formation of coke. This is the advantage: smaller crystals, shorter fusion pathways, improve accessibility, and we hope that we have a better resistance to coke. There is a beautiful review from Svetlana Mintova and Valentin Valchev and Nanoscale on 2013 about all the preparation routes which are available for nano-sized zeolite. And there are some conventional high organic templates to stabilize the materials. There are some organic free routes, dry gel conversion, seed assistant approaches. I don't want to go in detail about all the things, you can read them. And there are some new ones: microreactor used, or microwave and sonification, ion synthesis, and the synthesis, the structure formation in confined spaces. My focus is now just on this tool. The aluminium-rich zeolites are very important catalysts in the FCC catalysis, and in some other things, they are really important. But it is accessible. But for the silica-rich zeolites, we need a huge amount of templates, for example. And we have low yields. And to separate nanoparticles from such a high alkaline suspension is really difficult. And sometimes the prediction of the expected crystal size are not possible in this hydrothermal techniques which are available at the moment. And therefore we are going to propose a new technique, densification. We are going to prepare spherical materials, and we are use the spherical materials as a reactor. I will explain this. These are the materials: nano-sized materials, mesoporous, silicon particles, variation of the Stöber process. And this is porosity. And then we are going to infiltrate this material with the template, because dilute them to a certain extent. Then we are going to do a steam-assisted crystallization, and suddenly what happens? All these particles collapse to smaller particles, and we are finally out of 600 nanometers, just 80, 60 nanometers crystals. And this is how we do this. Certainly the preparation of this nano-sized precursors are not that easy. This is a Stöber process, the filtration process, then the calcination. We are going to reduce, we have the particles, we are going to infiltrate them, we dry them, and then we do a steam-assisted crystallization. We are putting them about water vapor, providing just a small amount of water via the vapor phase, and then we are going to transform them, and finally have nearly high materials, nano-sized materials at high concentration. And the temperature size of them is just 110 degrees. Usually you need 170 to 200 degrees for this procedure. Just to explain this is the diffraction pattern of this nano-sized precursor. These are the pores in the materials, steam assisted. We are going to the densified product is typical NFI type material. This is higher type, zeolite type what we want, and here you see the SEM picture of these materials. If you go now a little bit deeper, characterization, this is the particle size distribution of the starting material. This is the absorption isotherm. This is the typical step to characterize the mesoporosity. Then the impregnation, nothing happens. But after the steam assisted, you have really a complete shift to lower than 100 nanometers. And certainly you see the diffraction pattern we show. and you have the typical microporous isotherm, and the increase at the end is related to the packing of this nano-sized particle. The kinetic, you see here with the starting materials, the precursor, 3 hours nearly nothing. You see some spikes there, 6 hours complete transform, and you see in the pattern here already very small, tiny pieces. And these tiny pieces are already completely transformed materials. After 6 hours, everything is over. And if you analyze this in a little bit more detail, you see after 3 hours, half of the particle amount is transformed already, and the other half will be formed. That means if in one of the particles the crystallization starts, this is that fast that you can't really observe them anymore. And the small angle scattering gives you some more information. I skip this a little bit through. This is the particles, the scattering curve for the starting materials, typically the pores, the particle size, and then this particle starts to form. Here in the end, in the white range, you see already some spikes. Then you see a broadening of the pores, and here the peak shows up at 85 nanometers, and this is still the start of the formation, small particles, and then you see 100 nanometer the particle size, and nothing in between, and just in the white range, the typical X-ray diffraction pattern of the crystal. And this you can see in the bright field image. This are the mesoporous particles with the diffraction curve. The distance is due to the porosity, pore diameter. This is a densified particle, and if you look here, you see really the planes of the MRI with the 0111 orientation, and you see here in the electron diffraction the typical pattern of the crystal. And this seems to be a single crystal in this particle. We can introduce also some aluminium to the variation, and even with different ratios, silicon to alumina. Alumina is really important for the catalysis. It's the carrier of the charge 25, 40, 80. And this is the preconditions for, let's say, cracking reactions. And we did this with the cumene to benzene, compared with the standard material, commercial material again, provided by Clariant Deutschland. And what you see here, you see the conversion for the commercial one against the aluminium 80, silicon to alumina 80. Here you see the silicon to aluminium ratio and the active sites in the ammonia TPD. And even if you have some small active sites in our, we have a higher yield and we have the high selectivity of these materials in this case. So, just this brings me to the summary of the second part. This combines principles of the densification, the strength of the steam-assisted crystallization and the pre-formed precursor. We can now prepare precursors of 400, 600, 800 nanometers, and we have the densification. So we can predict the final size of our nanoparticles. So that's oops, not too fast. I didn't want to show this. No. We could reduce the template, and we need just this amount of template. We don't have any template in solution. We have a high yield of nanocrystal. Everything is transformed, and we have a very short crystallization time, and we can even predict the final crystal size due to the pore volume. But the future is a little bit. We can really encapsulate also platinum or other species in the spores before we do the densification. And this I would like to show here. And what you see here is a very nice pictures provided by our material department. And what you see here is really the spikes which you see here in this material is platinum, very well dispersed in a single crystal, nano single crystal but we have two spikes and platinum inside of the metal. And this is a little bit like an outlook. This brings me, and I have to thank the group of Erdmann Speaker and Benjamin Kinder for this wonderful terms and electron diffraction results, and Mr. Unruh for this Sachs measurement, and my students Albert Machober, Tobias Weiter, Eisenberger, and Bastian Weipert. And there are some bachelor and master students involved in this topic, and certainly there are some founders, the DFG, State of Bavaria, and the Helmholtz Association, and which I have to thank, and I have to thank you for your kind attention. Thanks.
Any questions?
So I have a very short question. So concerning your high-loaded platinum materials, so you have gone up to 28% platinum. As you know, platinum is very expensive. Do we really need 28% platinum?
No, this is just a proof of the concept. What we could do maximum to even under the condition of calcination to stabilize in this environment the radium particle. So we can really adjust now every loading which you want due to the equilibrium system. Ion exchange is very good to the equilibrium. You can introduce 1%, 2%, whatever you want, wait long enough to find the right conditions and load them.
And what you said, there is also coking. What is the amount of coke deposit? Did you estimate? CH&N, something like this?
I don't have it at the moment in my mind,
Okay.
but we can check it. I have it on some slides. Maybe tomorrow I give some slides about it.
Thank you.
Really, it looks very interesting. A single crystal nanostructure.
Yeah.
Do you have a more of, I would say, measured dimensions of how much dimension we're talking about? What about the planes of that single crystal looks like?
The plane of the single crystal, I showed it.
The one that you showed the simulation about it. Do you have any experimental data about, beside the simulated video that you showed at the very end?
At the very end.
Yes.
If you have more of this material,
About the facets of this single crystal.
I can't tell you. We can see the traction pattern in the temps, yeah,
Okay.
and
You have mentioned the 001, if I remember.
the 011.
The 011.
011
So this is
is
the only facet that shows on the crystal, or?
At least in the tem we see this.
Okay.
Yeah, but no, there must be certainly some other passages. Yeah. But they are very small. This is 50 nanometers, something like this. Yeah.
Any question? Thank you.